Have you ever tried to imagine what fast really means? Not a jet, not a rocket, but something so quick that it can cross the space between the moon and Earth in about a second. The speed of light isn't just a big number we memorize. It's a kind of boundary written into the structure of the universe. Try to picture chasing a beam of light, reaching for it, matching its pace. What would you see? Would time feel the same? Would distance still mean what it does now? If questions like that make you lean in a little closer, feel free to gently like and subscribe so more space-curious minds can join us. Now, settle in as we explore what really happens when you try to catch the fastest thing we know. To understand the nature of light, we must first look back to a time before it could travel. In the very beginning, there was no darkness as we understand it today, because darkness implies the absence of something that could be seen. In this initial state, there was simply nothing to see and no vantage point from which to look. There were no stars, no galaxies, and no empty space to separate them. The entire cosmos was compressed into a single point of infinite density and temperature. This was a state of pure, concentrated energy, waiting for the mechanism of time to begin. Then, the expansion occurred. It was not an explosion in the way we think of a bomb detonating inside a room, because there was no room for it to explode into. Instead, space itself began to stretch, carrying energy with it. In the first fraction of a second, a span of time so brief it defies human comprehension, the universe grew from the size of a subatomic particle to something vast. This rapid expansion created a chaotic soup of particles, quarks, electrons, and other fundamental building blocks of matter smashed into each other with violence and heat. In this early era, the universe was opaque. It was a dense, hot fog of plasma. Light existed in the form of photons, but these particles were prisoners of the chaos. Every time a photon tried to move, it would almost immediately collide with a free-floating electron. Imagine trying to run in a straight line through a crowd that is packed shoulder to shoulder. You would constantly bounce off others, unable to gain momentum or direction. This was the fate of light for the first few 100,000 years. It was a trap of endless collisions, a glowing fog where information could not travel. The universe was bright, but it was not clear. As time passed, the violence began to subside. The universe continued to expand, and as it grew larger, the energy spread out, causing the temperature to drop. After approximately 380,000 years, the cosmic thermometer fell to about 3,000 degrees Celsius. This specific temperature was a critical threshold. It allowed for a fundamental shift in the structure of matter. The frantic electrons slowed down enough to be captured by protons, forming the very first neutral atoms of hydrogen and helium. This event is known as recombination. It changed everything. With the electrons now bound securely into orbits around atomic nuclei, the space between atoms became clear. The obstacles were removed. For the first time, photons could travel in straight lines without being scattered. The fog lifted. In an instant, the universe became transparent, and light was released to stream across the cosmos. This moment was the first true flash of illumination, a release of energy that is still traveling today. We can still detect this ancient light. Over the course of 13.8 billion years, the expansion of the universe has stretched space itself, and with it, the wavelengths of that original light. What began as a visible orange glow has been pulled apart into longer, invisible waves of microwave radiation. Scientists call this the cosmic microwave background. It is a faint signal that fills every corner of the sky, arriving from all directions with almost perfect uniformity. If you were to tune an old analog television or radio between stations, a small percentage of the static hiss you hear and see is actually the physical interaction with these ancient photons. It is the afterglow of the Big Bang, a fossil of light that reminds us of the universe's hot, dense origin. But what exactly is this thing we call light? It is one of the most complex puzzles in physics. Light behaves as both a particle and a wave, a concept known as wave-particle duality. It is a ripple in the electromagnetic field, yet it also comes in discrete packets of energy called photons. These photons have zero mass. Because they have no mass, they do not need time to accelerate. From the exact moment a photon is created, whether inside a distant star or from the flashlight in your hand, it is already moving at top speed. It never rests. It never slows down, unless it passes through a medium like water or glass. And even then, it returns to its maximum velocity the moment it exits back into a vacuum. This constant motion connects you to the history of the cosmos. The light entering your eyes at this very moment carries energy that has traveled through the void to reach you. In a biological sense, you are a construct of this energy. The atoms in your body were forged in the cores of ancient stars, which exploded and scattered their matter across the galaxy. The energy that powers your cells comes from the food you eat, which relies on plants, which in turn rely on the capture of sunlight. The chain of energy remains unbroken. The sun warms the atmosphere, drives the weather, and dictates the rhythm of sleep and wakefulness. You are not just an observer of light, you are a participant in its flow. Yet, despite its ubiquity, light remains elusive. It is the fastest thing in the universe, the cosmic speed limit that dictates the flow of cause and effect. This absolute limit leads to a question that has fascinated physicists for over a century. What happens if you try to catch it? This is not just a playful question. It is the foundation of the theory of relativity. Let us conduct a thought experiment. Imagine you are no longer bound by the limitations of human biology or modern engineering. You are drifting in deep space, far from the gravitational pull of any planet. You decide to pursue a beam of light. In our everyday experience, speeds are additive. If you are in a car traveling at 60 miles per hour and another car passes you at 70 miles per hour, from your perspective, the other car is only moving away at 10 miles per hour. It seems logical that if you could move fast enough, you could pull up alongside a beam of light and match its speed. You might imagine seeing the light wave frozen beside you, stationary in space. However, the universe does not adhere to this logic. Light travels at a constant speed of exactly 299,792 kilometers per second. That is roughly 186,000 miles per second. If you were to accelerate your spaceship to half that speed, and then measure the speed of the light beam ahead of you, you would expect it to appear slower, but it does not. It still races away from you at exactly 299,792 kilometers per second. You accelerate further, reaching 99% of the speed of light. You look out the window again. The light is still moving away from you at the exact same constant speed. It has not slowed down relative to you by even a fraction. This creates a paradox. If the speed of light is constant, regardless of how fast you move, then something else must change to accommodate this fact. That something is time itself. As you accelerate toward the speed of light, the ticking of the clock on your wrist begins to slow down relative to a clock that is sitting still. This is called time dilation. At everyday speeds, this effect is negligible. But as you approach the speed of light, the effect becomes extreme. If you could travel at 99.5% of the speed of light for every year that passes for you on the ship, 10 years might pass for observers back on Earth. You are not just traveling through space, you are traveling through time at a different rate than everyone you left behind. The environment outside your ship would also begin to distort. Space itself is not rigid, it is flexible. As you reach these immense velocities, you would experience length contraction. The distances ahead of you would physically shrink. A journey that should take 100,000 light years might, from your perspective, feel like it takes only a few weeks, because the space you are traveling through has compressed in the direction of your motion. Visually, the universe would shift. The light coming from the stars ahead of you would be compressed into higher frequencies, turning blue, then violet, and eventually shifting into invisible ultraviolet and X-rays. This is the Doppler effect, applied to light. Behind you, the light from the stars would stretch out, turning red, then fading into infrared and radio waves, eventually disappearing into darkness. Your field of view would change, concentrating the light ahead into a bright, piercing beacon while the rest of the sky fades. But no matter how much energy you use, you can never reach the speed of light itself. To do so would require an infinite amount of energy, which is impossible. Light holds its position as the unreachable limit. But let us take the thought experiment one step further into the abstract. Imagine, for a moment, that you could break the laws of physics. Imagine you actually caught the photon, or better yet, imagine you became the photon. What is the experience of light itself? From the perspective of a photon, the concepts of space and time dissolve. Because light travels at the speed limit of the universe, it does not experience the passage of time. For a photon emitted by a star in the Andromeda Galaxy, 2.5 million years pass on Earth before it reaches us. But for the photon itself, the journey is instantaneous. The moment of its birth and the moment of its death, when it hits your eye, are the same moment. It traverses vast distances of the universe without aging a single second. To be light is to exist in a state of timelessness. There is no waiting, no duration, no history. There is only the connection between the source and the destination. This is a realm of physics that is entirely alien to our human experience. We are creatures of mass. We are defined by the passage of time, by the aging of our cells, by the sequence of before and after. We are anchored to the slow, steady ticking of the clock. So, the chase reveals a fundamental truth. We are made of matter, and matter is imprisoned by time. We can never truly catch light, because to do so would require us to leave behind the very structures that define our existence. We cannot run alongside the photon, frozen in a timeless moment. Instead, we are the observers. We are the ones who wait in the flow of time, watching the light arrive, letting it carry information from the past into our present. Perhaps the goal is not to catch the light, but to understand what its speed tells us about the reality we inhabit. The speed of light is not just a number. It is the structure that holds space and time together. It defines the causality of the universe. It ensures that effects follow causes. By trying to chase it in our minds, we learn the boundaries of our own reality. We learn that time is not absolute, that space is not fixed, and that our perspective is just one of many possible ways to view the cosmos. We remain here, in our stream of time, observing the constant, ageless messenger that connects us to the beginning of everything. The journey through the cosmos is often a journey of the mind. You have returned from that mental sprint, breathless, not from exertion, but from the implications of what you have just witnessed. You did not catch the photon. It remains elusive, always one step ahead, always out of reach. But in failing to catch it, you have stumbled upon something far more significant. You have touched the rigid edge of reality. Why does the universe behave this way? Why is the speed of light the one thing that refuses to compromise? In our daily lives, almost everything is relative. Speed usually depends on who is watching. If you are walking down the aisle of a moving train, your speed is one thing to the passenger sitting next to you, and something entirely different to the person watching from the platform as the train rushes by. To the passenger, you are moving at a slow walk. To the observer outside, you are moving at the speed of the train plus the speed of your walk. The velocities add up. It is intuitive. It makes sense. But light does not follow these rules. Light is the rebel of the physical world. Imagine you are floating in deep, empty space again. This time, you are holding a simple flashlight. You click it on. A beam of pure white light shoots out into the darkness. We know from measurements that this beam travels away from you at roughly 300,000 kilometers per second. Now, imagine you start moving. You attach a powerful engine to your back and accelerate until you are flying through space at half the speed of light, 150,000 kilometers per second. You point the flashlight forward and click it on again. Common sense tells you that the light should now be traveling faster. The speed of your flight plus the speed of the light should equal 450,000 kilometers per second. But it does not. The beam still travels away from you at exactly 300,000 kilometers per second. It is as if your own speed does not matter at all. The light is completely indifferent to your motion. This stubbornness was a source of great confusion for physicists in the late 19th century. They assumed light must travel through something, just as sound travels through air or waves travel through water. They called this invisible substance the luminiferous ether. They believed the ether filled all of space, providing a medium for light waves to ripple through. Scientists spent years building precise instruments to detect the wind of this ether as the Earth moved through space. They expected to see light speed up or slow down, depending on the direction of Earth's travel, but they found nothing. The experiments failed again and again. There was no ether. There was no wind. Light was traveling through a vacuum entirely on its own, at a constant speed, no matter which way the Earth was moving. It was a crisis in physics. The math didn't add up. The universe seemed to be breaking its own rules. Then, in 1905, a young patent clerk named Albert Einstein proposed a radical solution. He suggested that we were looking at the problem backward. He proposed that the speed of light is not just a speed. It is a fundamental constant of nature. It is the fixed pivot point around which the rest of the universe turns. If the speed of light must remain constant, then everything else, space and time, must change to accommodate it. This was the birth of the special theory of relativity. It suggests that space and time are not the rigid, unchanging stage on which the events of the universe play out. Instead, they are flexible, they are dynamic. To keep the speed of light constant for all observers, space must shrink and time must slow down. Think about the implications of this. It means that reality is subjective. Two observers moving at different speeds will disagree on the length of a meter stick. They will disagree on the duration of a second, and both of them will be correct. There is no master clock. ticking in the center of the universe. Every object, every person, every atom carries its own time, inextricably linked to its motion through space. This is not just abstract theory, it is a practical reality that affects the technology you use every day. Consider the Global Positioning System, or GPS, that guides you to your destination. There is a constellation of roughly 30 satellites orbiting the Earth at an altitude of about 20,000 kilometers. These satellites are moving fast, about 14,000 kilometers per hour. Because of their speed, time for these satellites ticks slightly slower than it does for clocks on the ground. This is a direct consequence of special relativity. Furthermore, because they are far away from Earth's heavy mass, gravity is weaker for them. According to general relativity, Einstein's later theory, time actually ticks faster where gravity is weaker. So, engineers have to calculate the balance between these two effects. The result is that the atomic clocks on GPS satellites tick faster than clocks on Earth by about 38 microseconds per day. 38 microseconds sounds like nothing. It is a fraction of a blink of an eye. But light travels so fast that in 38 microseconds, it covers about 11 kilometers. If engineers did not program the satellites to correct for this difference in time, the GPS in your car or phone would drift by kilometers every single day. Within weeks, the system would be useless. The fact that your map app knows exactly where you are is proof that time is relative and that the speed of light is the ruler by which we measure reality. So, light is the great equalizer. It is the one thing all observers in the universe can agree on. Imagine two spaceships drifting past each other in the void. The pilots cannot agree on who is moving and who is standing still. They cannot agree on how much time has passed. But if they both measure the speed of a passing light beam, they will get the exact same number. This shared constant is what allows the laws of physics to remain consistent throughout the universe. It ensures that the chemistry that happens in a test tube on Earth is the same chemistry that happens in the atmosphere of a distant exoplanet. Without this constancy, the universe would be a chaotic, unpredictable place where the laws of nature shifted depending on how fast you were moving. But as we accept this truth that light is constant, we must accept the strange consequence that follows. If light is the rock-solid foundation, then time is the shifting sand. We are used to thinking of time as a steady river, flowing at the same pace for everyone, everywhere. We structure our lives around the ticking of the clock. Seconds, minutes, hours, they feel absolute, but they are not. Tonight, we begin to dismantle that intuition. We begin to see time not as a universal metronome, but as a personal experience. It is elastic, it stretches, it compresses. Let us drift into this idea of time dilation. It sounds like science fiction, but it is science fact. Imagine you are an astronaut. You board a sleek, futuristic spaceship capable of reaching 90% of the speed of light. You leave Earth behind, waving goodbye to your twin sibling who stays on the ground. You travel to a nearby star, loop around, and come back. For you, on the ship, everything feels normal. You eat your meals, you sleep, you read books, your heart beats at its normal rhythm. Your watch ticks forward, 1 second at a time. The journey, by your internal clock, takes perhaps 5 years. You have aged 5 years. Your cells have divided for 5 years. You have 5 years of memories. But when you land back on Earth and open the hatch, you find a world that has changed. Your twin sibling is not 5 years older. They are 10 or 20 or 50 years older, depending on how close to light speed you traveled. While you were gone, decades passed on Earth. Governments changed, children grew up, technology evolved. You have effectively traveled into the future. This is the twin paradox, a famous thought experiment in physics. It highlights the pliability of time. The faster you move through space, the slower you move through time. It is as if you have a fixed budget of motion. You can spend it all moving through time, which is what we do when we are sitting still, or you can trade some of that motion through time to move through space. The more you spend on space, the less you have for time. At the speed of light, the trade-off is complete. A photon spends all its motion on space and none on time. That is why light does not age. That is why the journey is instantaneous for the beam itself. This concept can be unsettling. It removes the safety net of a shared now. There is no universal now that applies to the entire universe simultaneously. My now and your now only align because we are moving at roughly the same slow speed on the same planet. If one of us were to speed up significantly, our nows would drift apart. But there is also a beauty in this. It means that your experience of time is uniquely yours. It belongs to you. It is defined by your path through the cosmos. You are not just a passenger on a train that is moving at a fixed speed. You are the conductor of your own temporal journey. Your gravity, your motion, your existence warps the flow of time around you. So, as you lie there, feeling the steady rhythm of your breath, remember that this rhythm is your own private clock. You are drifting through the fourth dimension time at your own pace. And while we are all bound by the speed limit of light, within that limit, there is infinite room for variation. We are all time travelers, moving forward into the future, each of us on a slightly different path, guided by the invisible, unbending rules of light. As you continue your theoretical acceleration through the cosmos, the visual landscape outside your window undergoes a dramatic transformation. This is not a hallucination induced by speed, but a physical shifting of the electromagnetic spectrum known as the relativistic Doppler effect. Ahead of you, the light waves emitted by stars are being compressed by your forward motion. As the distance between the crests of these waves shortens, their frequency increases. Visually, this shifts the stars from yellow or white into the blue spectrum, then to violet, and finally into invisible ultraviolet and X-rays. The universe ahead becomes brighter and more energetic. Conversely, behind you, the light waves are stretched out, their wavelengths elongate, shifting the starlight into red, then infrared, and eventually fading into the dark silence of radio waves. You are suspended between a high-energy beacon ahead and a fading void behind. This distortion reminds us that your experience of reality is entirely dependent on your frame of reference. Even now, in what you consider a stationary state, you are in motion. The Earth rotates at the equator at roughly 1,000 miles per hour. It orbits the Sun at approximately 67,000 miles per hour. The solar system itself orbits the center of the Milky Way galaxy at nearly 500,000 miles per hour. There is no such thing as truly standing still. Consequently, your experience of time is already uniquely yours, slightly different from that of an observer in a different galaxy. Though the difference at these slow speeds is negligible, however, as you approach the speed of light, these subtle differences become the dominant laws of existence. We have established that time slows down for the traveler, but time is not the only variable in Einstein's equations. Space itself is equally pliable. This brings us to the phenomenon of length contraction, often called Lorentz contraction. It dictates that for an object moving at a significant fraction of the speed of light, the physical distance in the direction of travel actually shrinks. To understand this, we must abandon the intuitive idea that space is a fixed stage. Imagine you are holding a standard meter stick. Inside your spaceship, relative to you, the stick remains exactly 1 meter long. You see no change. But to an observer watching you fly past from a stationary asteroid, that same meter stick would measure less than 1 meter. At 87% of the speed of light, they would measure it as half a meter. At 99.5% of the speed of light, it would appear to be only 10 centimeters long. Crucially, this contraction only happens in the direction of motion. The meter stick does not get thinner or shorter in height. It only compresses along the line of your path. This sounds like a mathematical trick or an optical illusion, but it is a physical reality that we observe in nature. The most compelling proof comes from subatomic particles called muons. Muons are created when cosmic rays crash into the upper atmosphere, about 15 kilometers above the Earth's surface. These particles are unstable and decay very quickly in about 2.2 microseconds. Even traveling near the speed of light, a muon should only be able to travel about 600 meters before it decays. Therefore, statistically, almost no muons should ever reach the ground. Yet, we detect them at sea level in great numbers. Why? From our perspective on Earth, this is explained by time dilation. Because the muons are moving so fast, their internal clocks run slow, allowing them to live long enough to reach the ground. But consider the muon's perspective. From its frame of reference, its lifetime is still only 2.2 microseconds. It does not feel time slowing down. So how does it traverse 15 kilometers of atmosphere in such a short life? The answer is length contraction. From the muon's point of view, it is not the muon that is moving. It is the Earth and its atmosphere rushing toward it. Because of this relative speed, the 15 kilometers of atmosphere contracts. To the muon, the distance to the ground is not 15 kilometers. It is only a few hundred meters. It can easily cross this shortened distance before it decays. Both perspectives, the observer on Earth seeing time stretch and the muon seeing space shrink, result in the exact same outcome. The particle hits the ground. The laws of physics remain consistent, but the mix of space and time required to achieve them changes depending on the observer. This is the mechanism that theoretically enables interstellar travel within a human lifetime. If you were to travel to a star system located 100 light years away, you might assume it would take at least 100 years to get there. But if you travel at 99.9% of the speed of light, length contraction takes over. The space between Earth and that star would physically shrink for you. The journey might feel like it takes only a few years or even months. You would arrive effectively having skipped over the vast distance. However, there is a trade-off. While the journey takes very little time for you, 100 years still pass on Earth. You essentially travel into the future. Now, consider the ultimate limit, the photon itself. We previously asked what it would be like to be light. We discussed that a photon experiences no time. Now we can add the spatial component. At the speed of light, the factor of length contraction becomes infinite. The entire distance of the universe, in the direction of the photon's travel, contracts to exactly 0. For a photon emitted by a distant galaxy billions of light years away, the distance to your eye is 0. The moment of emission and the moment of absorption are spatially identical. In the photon's reference frame, It does not travel across the universe. It connects two points that are touching. This is why light does not age and does not experience duration. It exists in a state where space has collapsed and time has stopped. For us, beings of mass, we can never reach this state. We are embedded in space that has volume and time that has duration. But as we move faster, we see the universe begin to fold. We see that distance is not an absolute barrier. Distance is a relationship between the observer and the destination, mediated by speed. This interplay suggests that space and time are not separate entities. They are two sides of the same coin. When you stand still, you move entirely through time. When you move through space, you borrow from your motion through time, and space responds by contracting. There is a balance, a conservation of movement through a four-dimensional structure. This realization that space acts like a dynamic fabric that curves, stretches, and shrinks leads us to the final unification. We need a term that encompasses both. We are no longer dealing with space and time as distinct stages. We are dealing with space-time. It is this unified fabric that bends to accommodate the constant speed of light. It is this fabric that we must now visualize to truly understand the architecture of the universe. We have spoken of flexible time and shrinking space, but what kind of mind could look at the solid, dependable world around us and see such fluidity? Who would dare to suggest that the universe is not a rigid box, but a dynamic, shifting fabric? To understand this, we must leave the abstract void of space and travel back to a very specific place and time. The year is 1905. The place is Bern, Switzerland. Imagine a quiet office. The room is filled with the smell of paper and ink. Outside the window, the city is moving into the modern age. Electric trams rattle down the cobblestone streets. Telegraph wires stretch across rooftops, carrying messages at invisible speeds. And everywhere, there are clocks, tower clocks, station clocks, pocket watches. The world of the early 20th century was obsessed with synchronizing time, with making sure the train leaving Zurich agreed with the clock in Bern. Sitting at a desk in the Swiss patent office is a 26-year-old clerk named Albert Einstein. He is not a famous professor. He has no team of graduate students. He is a technical expert, third class, spending his days reviewing applications for new devices, typewriters, cameras, and systems for synchronizing electric clocks. While his hands worked on these practical inventions, his mind was drifting through the cosmos. Einstein was troubled by a contradiction that had been ignored by the greatest physicists of his time. He went back to that childhood question: what happens if I chase a beam of light? According to the physics of Isaac Newton, which had ruled science for 200 years, if you chased a beam of light at light speed, you should see the light waves frozen beside you, stationary in space, like ripples in a frozen pond. But the equations of James Clerk Maxwell, which described electricity and magnetism, said this was impossible. Maxwell's math showed that light must always move. It cannot stand still. So, Einstein sat with this paradox. A frozen wave was impossible, yet catching up to light seemed logical. Something had to give. Most scientists thought the math was wrong. Einstein, with a quiet audacity, decided that our understanding of reality was wrong. He realized that if the speed of light is the immutable law, the one thing that never changes for any observer, then the things we think are constant must be the ones to change. Time is not absolute. Distance is not absolute. They are merely shadows cast by the speed of light. This was the birth of the special theory of relativity. The name special refers to the fact that it deals with a special case, motion in a straight line at a constant speed, without gravity or acceleration. In this theory, Einstein unified the universe. Before him, we had space, the stage, and time, the clock. Einstein stitched them together into a single four-dimensional fabric called space-time. He also unified mass and energy. From his papers emerged the most famous equation in history, E equals mc squared. Let us pause to truly understand what this means. E stands for energy, I'm stands for mass, c is the speed of light. The equation says that energy is equal to mass multiplied by the speed of light squared. Because the speed of light is a huge number, its square is an astronomically huge number. This means that even a tiny amount of mass contains a tremendous amount of potential energy. It tells us that mass is simply frozen energy. A rock, a drop of water, a pencil, they are all concentrated packets of energy waiting to be released. This is the mechanism that powers the sun. In the solar core, hydrogen atoms smash together, losing a tiny fraction of their mass. That lost mass is converted into pure energy, radiating out as heat and light that sustains life on Earth. Einstein's revolution was quiet. There were no press conferences, no fireworks. He simply published his papers in a physics journal and waited. At first, the world ignored him, but slowly, the truth of his ideas began to permeate the scientific community. He had not just solved a puzzle about light, he had rewritten the operating system of the universe. And so, we come to the question of the limit itself. If Einstein is right, and light is the ruler of space-time, what happens if we try to break the rule? What happens if we try to go faster? This brings us to the cosmic speed limit. In our human experience, limits are usually things we can overcome. We build faster cars to break land speed records. We build rockets to break the sound barrier. We assume that with enough power, we can break the light barrier too. But the speed of light, 299,792 kilometers per second, is not a barrier like the sound barrier. The sound barrier is just air resistance piling up. The light barrier is a fundamental property of geometry. As you accelerate an object, let's say your spaceship, you pour energy into it. At low speeds, that energy goes into making the ship move faster. But as you get closer to the speed of light, the rules of relativity shift. The energy you add stops increasing your speed and starts increasing your relativistic mass. Technically, physicists prefer to say your momentum increases without bound, but the effect is the same. The faster you go, the heavier and harder to push you become. At 99% of light speed, you are incredibly heavy in terms of energy. To push that final 1%, to reach the speed of light, you would need an infinite amount of energy. Since there is not an infinite amount of energy in the universe, you can never reach the speed of light. You can get closer and closer, 9999%, but you can never touch the limit. Why is the universe built this way? Is it a flaw? A constraint? Actually, it is a protection. This speed limit is the guardian of causality. Causality is the simple rule that the cause must happen before the effect. You must strike the match before the fire starts. You must drop the glass before it shatters. If you could travel faster than light, the equations of relativity show that you could theoretically travel backward in time. You could arrive at a destination before you left. You could see the glass shatter before you dropped it. The universe would descend into chaos. Effects would precede their causes. history would unravel. The speed of light limits how fast information can travel. It ensures that every event in the universe has a definite order. When the sun emits a photon, it takes 8 minutes and 20 seconds to reach Earth. That delay is the glue of reality. It ensures that the universe is not happening all at once, but unfolding in a sequence that makes sense. So, the speed limit is not a cage. It is the structure that allows the universe to exist as a coherent place. It allows stars to burn slowly over billions of years instead of exploding instantly. It allows gravity to propagate at a set speed, keeping galaxies in graceful rotation. It allows for the existence of the now, the before, and the after. We, as beings of mass, live within this limit. We are creatures of the slow lane, and that is exactly where we need to be to exist. The photon, timeless and massless, zips along the edge of reality, stitching the cosmos together. We, comfortably heavy and slow, get to experience the passage of time, the unfolding of a life, the beauty of a duration. Einstein showed us that this limit is not something to be conquered. It is something to be understood. It is the fundamental constant that makes the universe a rational home for matter, for energy, and for life. We have established the speed of light as the absolute limit of the cosmos. But if we stop looking at the speedometer and start looking at the traveler itself, a deeper mystery emerges. What exactly is this thing we call light? Is it a solid object like a microscopic marble, or is it a ripple like a wave on a pond? The answer is one of the most unsettling truths in physics. Tonight, let us drift into the subatomic realm to meet the photon. Picture yourself floating in the void again. Around you, there is silence, but across the darkness, energy is moving. It does not drift like smoke. It shoots forward with absolute precision. A photon is a quantum of light. The word quantum implies a specific, discrete packet. You cannot have half a photon. It is an indivisible unit of energy. In this sense, light behaves like a particle. It hits a solar panel and knocks an electron loose, generating electricity. It strikes the retina of your eye and triggers a chemical signal to your brain. It acts like a tiny projectile, delivering its energy in a single, localized impact. Yet, this projectile has no mass. A baseball has mass. A grain of sand has mass. Even an electron has mass. But a photon is pure energy in motion. Because it is massless, it cannot sit still. A rock can rest on the ground, but a photon exists only at speed. The moment it is born, whether from a candle flame or a supernova, it is already moving at 300,000 kilometers per second. It does not accelerate. It just is. And the moment it stops moving is the moment it ceases to exist, absorbed by an atom and converted into heat or chemical energy. But if you try to measure where this particle is, the picture blurs. This is because light is also a wave. It is an oscillation in the electromagnetic field. As it travels, it ripples. It has peaks and valleys. It has a frequency. This duality, being both a particle and a wave, is not just a figure of speech. It is a fundamental property of nature that was demonstrated in the famous double-slit experiment. Imagine a barrier with two narrow vertical slits cut into it. Behind the barrier is a detector screen. If you were to fire tiny solid marbles at the barrier, they would pass through the slits and form two distinct vertical bands on the back screen. This is particle behavior. Now, imagine shining a light through those slits. If light were just particles, you would expect two bright lines on the screen. But that is not what happens. Instead, you see a series of alternating bright and dark stripes. This is an interference pattern. It happens because the light waves passing through the two slits ripple out and overlap. Where two crests meet, they amplify each other. Bright stripe. Where a crest meets a trough, they cancel each other out. Dark stripe. This proves light is a wave. But here is the twist. If you fire photons one at a time, single particles, separated by seconds, they still build up this interference pattern over time. How can a single photon interfere with itself? It is as if the single particle passes through both slits at once, explores all possible paths, and then interferes with its own potential existence. And if you place a detector at the slits to watch which hole the photon actually goes through, the interference pattern disappears. The light suddenly behaves like simple marbles again, forming two boring lines. The act of observation collapses the wave possibilities into a single particle reality. This suggests that the photon is not a fixed thing until it interacts with something. Until it hits your eye or a detector, it is a ghost of probability, a wave of potential. This wave nature is also what gives us color. A photon is not inherently red or blue. It carries energy. If the waves are packed tightly together, a short wavelength, our eyes interpret that high energy as blue or violet. If the waves are long and lazy, we see red. Stretch them further, and they become infrared, which warms your skin but is invisible to your eye. Stretch them even more, and they become radio waves, passing through walls to bring music to your car. Compress them tightly, past violet, and they become X-rays that pass through soft tissue. All of these radio, infrared, visible light, X-rays, gamma rays are the exact same thing, photons. The only difference is how much energy they carry and how fast they vibrate. They all travel at the same constant speed. So, you are not just seeing light. You are seeing the energy levels of the universe. Now, let us take this understanding of light and motion and apply it to the human experience. We return to the consequences of moving near light speed, specifically regarding time. This brings us to the twin paradox. This is a thought experiment that helps us grapple with the reality of time dilation. Imagine two twins, born on the same day, identical in every way. Let's call them Terra, who stays on Earth, and Astra, who travels to the stars. Terra remains on Earth. She lives a normal life. She feels the gravity of the planet, watches the seasons change, and her biological clock ticks in sync with the rest of the world. Astra boards a spaceship capable of constant acceleration near the speed of light. She travels to a star system 10 light years away. To her, inside the ship, everything feels normal. She eats, sleeps, and reads. Because of length contraction, the distance to the star shrinks for her. The journey that covers 10 light years of space might only take a few months of her personal time. She arrives, turns the ship around, and flies back. When Astra lands on Earth and steps out of the airlock, a shock awaits. She is aged perhaps 2 years, but Terra, her twin sister, is an old woman. 20 or 30 years might have passed on Earth. How is this possible? And why is it not reversible? Relativity says motion is relative. From Astra's perspective, wasn't Earth moving away from her? Why didn't Terra stay young? The answer lies in the journey itself. The situation is not symmetrical. Terra remained in a single, inertial frame the entire time. She never felt a change in motion. Astra, however, had to accelerate to leave Earth. More importantly, she had to turn around to come back. She had to decelerate, stop, and accelerate back toward Earth. That moment of turning around is the key. When Astra changes direction, she shifts from one frame of reference to another. She physically feels the force of the turn. In that shift, her path through space-time takes a shortcut. Think of space-time as a piece of paper. Terra draws a straight line from the bottom to the top. That is her path through time, long and steady. Astra draws a line that goes out at an angle and then zigs back to meet the top. In geometry on paper, the straight line is the shortest distance. But in the geometry of space-time, the rules are inverted. The straight path, staying still in space, covers the most distance in time. The bent path, moving fast through space, covers less distance in time. So, Astra literally took a shortcut through the fourth dimension. She experienced less duration. This is not a biological trick. It is a physical reality. Every atom in Astra's body vibrated fewer times than the atoms in Terra's body. Her heart beat fewer times. Her cells divided fewer times. She is physically younger because she existed for less duration. This leads to a profound realization about existence. We tend to think of now as a universal sheet that covers the whole universe at once. We imagine that right now, it is the same moment in the Andromeda Galaxy as it is here. But the twin paradox shows us that this is false. Now is local. Now is a bubble that you carry with you. Your passage through time is defined by your motion through space. We are all time travelers, drifting forward at different rates. Usually, on Earth, our speeds are so similar that our clocks stay in sync. But if we ever reach the stars, if we ever build ships that ride the edge of light speed, we will have to say goodbye to the shared present. Families will be separated not just by distance, but by decades of time. A father could leave on a voyage and return to find his daughter is older than he is. This is the price of speed. The faster you move through space, the slower you move through time. The photon, moving at the ultimate speed, pays the ultimate price. It experiences no time at all. For us, the slow movers, time is the dominant experience. We age, we remember, we wait. So, as you lie there, consider your own path through space-time. You are moving along your own world line. It is unique to you, and while we cannot jump into spaceships to stay young, we can appreciate the strange, elastic fabric of reality that makes such things possible. We are woven into a universe where time is not a master that rules us, but a dimension that we travel through, shaped by the very energy of our motion. We have explored the speed of light and the dilation of time. Now, we must examine the messenger itself. When we look at the world, we assume we are seeing everything there is to see. We trust our eyes to reveal reality. But in the grand scheme of physics, the human eye is an incredibly limited instrument. We are effectively looking at the universe through a keyhole. What we call color is simply the way our brains interpret the wavelength of light. Light is a wave of electromagnetic energy. The distance between two peaks of that wave determines its identity. Our eyes are tuned to detect wavelengths between approximately 380 nanometers, violet, and 700 nanometers, red. That is the entire visible spectrum. It is a tiny, narrow band amidst a vast ocean of radiation. If we were to widen our perception, the universe would transform. Let us begin by sliding down the scale to waves that are longer than what we can see. Just past the color red lies the infrared. Infrared waves are longer and carry less energy than visible light. While your retina cannot detect them, your skin can. You experience infrared primarily as heat. Every object in the universe that is not at absolute zero emits infrared radiation. An ice cube, a stone, your own body, all are glowing with thermal light. If you could switch your vision to infrared, the darkness would vanish. You would see the warm engine of a car parked hours ago. You would see the blood flowing beneath the skin of a person standing in the shadows. In astronomy, infrared is crucial because these long waves can pass through dense clouds of cosmic dust that block ordinary light. By using infrared telescopes, scientists can peer inside these dusty cocoons to watch the birth of new stars. Stretch the wave further, and you enter the realm of microwaves. These waves range from 1 millimeter to 1 meter in length. They are the frequency at which water molecules vibrate, which is why we use them to heat food. But they also carry the oldest secret in the cosmos. The cosmic microwave background radiation is the afterglow of the Big Bang, cooled down over billions of years, filling the sky with a faint, uniform static that is invisible to the naked eye but detectable by radio antennas. Stretch the wave even further, and we arrive at radio waves. These are the giants of the spectrum. A single radio wave can be as long as a football field or even stretch for kilometers. Because they are so large, they can bypass obstacles like buildings and mountains and pass through the atmosphere without being scattered. This makes them perfect for communication. When you listen to music in your car or receive data on your phone, you are essentially seeing invisible light that has been modulated to carry information. Now, let us return to the visible band and move in the other direction, toward higher energy. Just past violet lies the ultraviolet. These waves are shorter than visible light, packed with more energy. This is the point where light begins to become dangerous to biological life. Ultraviolet photons have enough energy to penetrate skin cells and damage the DNA inside, causing sunburns. Yet, this light creates a hidden landscape in nature. Many flowers have ultraviolet patterns on their petals, bullseyes, and runways that direct bees toward nectar. We see a plain yellow flower. The bee sees a glowing target, shorten the wave further, and we reach X-rays. These wavelengths are roughly the size of an atom. Because they are so small and energetic, they pass straight through the soft tissues of your body, which are made of light atoms like carbon and water. However, they are blocked by the denser calcium atoms in your bones. When a doctor takes an X-ray, they are essentially casting a shadow of your skeleton using high-energy light. Finally, at the extreme end of the spectrum, we find gamma rays. These are the most energetic form of light in the universe. They are produced by the most violent events imaginable: the explosion of supernovas, the collision of neutron stars, and the decay of radioactive atoms. Gamma rays have wavelengths smaller than the nucleus of an atom. They are piercing and destructive, capable of sterilizing life. Fortunately, Earth's atmosphere absorbs the vast majority of gamma rays from space, protecting us from this cosmic radiation. So, light is not just one thing. It is a continuous spectrum, from the kilometer-long radio wave to the subatomic gamma ray. They are all photons. They all travel at the exact same speed. The only difference is their energy and their wavelength. We are bathed in this invisible sea every moment of our lives. But where does this light come from? And how does it carry the history of the universe? To understand the journey of a photon, we must look into the heart of a star. Let us take our own sun as the example. Deep in the core of the sun The pressure is 250 billion times greater than Earth's atmosphere. The temperature is 15 million degrees Celsius. In this crushing environment, hydrogen atoms are smashed together with such force that they fuse into helium. This process, nuclear fusion, converts a tiny amount of mass into pure energy, following Einstein's equation. That energy is released as a high-energy gamma-ray photon. You might imagine that this photon instantly zips out of the sun and flies to Earth. But the reality is far more difficult. The core of the sun is incredibly dense. It is packed so tight with protons and electrons that the photon can only travel a tiny fraction of a millimeter before it crashes into a particle. When it crashes, it is absorbed and then immediately re-emitted in a random direction. This happens over and over again. Bounce, absorb, emit, bounce, absorb, emit. This process is called the random walk. The photon behaves like a lost traveler in a dense forest, constantly changing direction. It might take a few steps outward, then get knocked backward. It struggles against the density of the star. It can take anywhere from 100,000 to 1 million years for that single photon to fight its way from the core to the surface of the sun. Think about that. The sunlight hitting your face today was created in the core of the sun before human civilization began. It has been trapping inside the star for eons. As the photon slowly works its way out to the cooler, less dense layers of the sun, it loses energy. It stretches out. What began as a deadly gamma ray in the core gradually shifts into an X-ray, then ultraviolet, and finally, as it breaches the surface, it emerges mostly as visible light and infrared heat. Once it breaks free from the sun's surface, the journey changes. The vacuum of space is empty. There are no obstacles. The photon, now free, races across the 150 million kilometers to Earth in exactly 8 minutes and 20 seconds. This journey highlights a profound truth. Light is a time capsule. Because light takes time to travel, we never see the universe as it is now. We only see it as it was. When you look at the moon, you see it as it was 1.3 seconds ago. When you look at Jupiter, you see it as it was roughly 40 minutes ago. As we look further, we look deeper into history. The nearest star system, Alpha Centauri, is 4 light years away. If it were to explode today, we would not know for 4 years. The light carrying the image of the explosion is still traveling toward us. The Andromeda Galaxy is 2.5 million light years away. The light we see from it left those stars when early ancestors of humans were just beginning to walk upright. Astronomers use this delay to study the evolution of the cosmos. By looking at galaxies billions of light years away, they are looking at the universe as it was billions of years ago. The telescope is a time machine. It allows us to reconstruct the life story of the universe by observing its infancy, its adolescence, and its maturity, all frozen in the transit of light. But light carries more than just images. It carries data. It carries the chemical fingerprint of its source. This brings us to the science of spectroscopy. In the 19th century, scientists passed sunlight through a prism, spreading it into a rainbow. They noticed something strange. The rainbow was not perfect. It was interrupted by hundreds of thin, dark, vertical lines. It looked like a barcode. These are called Fraunhofer lines. They are caused by atoms in the sun's atmosphere. As light from the core passes through the cooler outer layers of the sun, different elements, hydrogen, helium, sodium, iron, absorb very specific wavelengths of light. Each element has a unique configuration of electrons, and these electrons only absorb specific energies. It is as if every element sings a specific note. When the light passes through, the atoms steal those specific notes, leaving black gaps in the spectrum. By analyzing these dark lines, astronomers can determine exactly what a star is made of without ever leaving Earth. We know there is iron in the sun, calcium in distant red giants, and oxygen in the atmospheres of exoplanets, solely by reading the missing slivers of light in their spectrums. We can also measure motion. If a star is moving away from us, its light waves are stretched out. The entire barcode shifts toward the red end of the spectrum. This is redshift. If it is moving toward us, the waves compress, and the barcode shifts toward the blue. This is how we know the universe is expanding. Almost every distant galaxy shows a redshift. They are all rushing away from us. The light tells us the story of a universe that is growing, stretching, and evolving. So, when you stand under the night sky, you are not just looking at pretty lights. You are standing in a rain of information. Photons are falling onto your retina that have traveled for millions of years, surviving the crush of stellar cores and the emptiness of the void, carrying with them the temperature, the composition, and the history of the stars that birthed them. You are connecting directly to the physical reality of the cosmos. The iron in your blood and the calcium in your bones were forged in stars that died long ago, and the light tells us exactly how it happened. We are not separate from the stars. We are intimately connected to them through the constant, silent stream of light. We have followed light from the birth of the universe to the smallest quantum flicker. We have seen it stretch time and shrink space. But there is one final interaction we must explore before we turn inward. We must ask, can light itself be bent? In the classical physics of Isaac Newton, light traveled in straight lines. It was weightless, and therefore, gravity, which was thought to be a force that pulled on mass, should have no effect on it. If you throw a ball, gravity pulls it down to Earth. If you shine a flashlight, the beam should cut through the universe perfectly straight, forever. But in 1915, Albert Einstein introduced the general theory of relativity, and he shattered this idea. Einstein proposed that gravity is not a force that reaches out and grabs things. Instead, he suggested that mass tells space how to curve, and space tells mass how to move. Imagine placing a heavy bowling ball in the center of a trampoline. The fabric dips down, creating a curve. If you roll a marble across the trampoline, it will curve around the bowling ball. It is not being pulled. It is simply following the shape of the fabric. Now, imagine that the marble is a photon, a particle of light. Even though the photon has no mass, it still has to travel through the fabric of space. If that fabric is curved by a massive star or a galaxy, the light must follow the curve. It has no choice. The straight line through curved space is actually a curve. This was a radical idea. It meant that starlight passing near the sun should bend. In 1919, astronomers put this to the test. During a total solar eclipse, the moon blocked the sun's glare, allowing scientists to see the stars located directly behind the sun. If Newton was right, the stars should be in their normal positions. If Einstein was right, the sun's gravity would bend the light from those stars, making them appear slightly shifted from their true locations. The result was historic. The stars had shifted. Space was curved. The universe was not a rigid grid. It was a fluid, malleable shape. This phenomenon is called gravitational lensing. Today, it is one of our most powerful tools. Massive clusters of galaxies act like giant glass lenses in the sky. They magnify and distort the light from objects behind them. If you look at deep field images from the Hubble or James Webb telescopes, you will often see strange arcs of light. These are not curved galaxies. They are normal galaxies whose light has been smeared into a circle, an Einstein ring, by the gravity of a massive object in the foreground. But the most extreme example of this bending occurs at the edge of a black hole. A black hole is an object so dense that it punctures a deep well in the fabric of space-time. At a certain distance from the center, gravity is so strong that light can actually orbit. This region is called the photon sphere. Here, if you were standing in the right spot, you could look forward and see the back of your own head, because the light reflecting off your back would circle the black hole and return to your eyes. Light, the fastest thing in existence, becomes a prisoner of geometry. It circles endlessly, caught in a trap not of force, but of curved space. Now, let us gently descend from these cosmic heights. Let us follow the light as it escapes the pull of gravity, travels across the void, and arrives at a much softer destination. You. We often think of light as something external, a tool we use to see, but biologically, light is a fundamental nutrient. We are photobiological beings. The journey of light into the human body begins at the skin. When sunlight strikes you, it is not just warming you, it is initiating complex chemistry. Specifically, ultraviolet B radiation penetrates the epidermis and strikes a molecule called 7-dehydrocholesterol. The energy from the photon breaks a chemical bond, transforming this molecule into pre-vitamin D3. This is a form of photosynthesis, not unlike what plants do. Your body harvests the energy of the sun to build the hormones necessary for bone health and immune function. Without this invisible interaction, our bodies would crumble. We are literally solar powered. Deeper still, light regulates the master clock of your existence. Buried deep in the brain, just above where the optic nerves cross, is a tiny cluster of cells called the suprachiasmatic nucleus. This is your circadian pacemaker. It does not need vision to work. It only needs brightness. Special cells in your eyes detect the blue wavelength light of the morning sky. When this signal hits the brain, it suppresses the production of melatonin, the hormone of sleep. It tells your body, it is day. Be alert. Digest food. Raise body temperature. As the sun sets and the light turns red and dim, the signal stops. Melanin flows into the bloodstream, lowering your temperature and inviting sleep. This is an ancient rhythm, billions of years old, shared by almost every life form on Earth. When we stare at bright phone screens late at night, we are flooding our eyes with artificial blue light, tricking this ancient clock into thinking it is noon. We disrupt the harmony between our biology and the planet's rotation. But the relationship goes even deeper. We are not just consumers of light, we are emitters of it. Every living cell in your body engages in metabolic reactions that release energy. Some of this energy is released as heat infrared light. This is why you glow in thermal cameras. But more surprisingly, scientists have detected that human cells emit ultra-weak photons in the visible spectrum, known as biophotons. This is not the result of heat. It is a quantum phenomenon happening within your mitochondria and DNA. You are faintly glowing in the dark. The light is too weak for the human eye to see, about 1,000 times weaker than the sensitivity of our naked eye, but sensitive cameras can pick it up. The glow fluctuates with the time of day, brightest in the afternoon and dimmest at night. We are, in a very literal sense, beings of light, The atoms in our bodies were forged in the nuclear furnaces of stars. The energy that moves our muscles came from the sun, captured by plants and transferred to us. And now, we know that we even emit our own faint starlight back into the void. So, when you close your eyes tonight, remember that you are not cutting yourself off from the light. You are simply turning your attention inward to the rhythms it is set in motion. You are a vessel of stored starlight, navigating a universe woven from space, time, and the radiant energy that connects it all. We have watched light bend around black holes and curve through the lenses of our own eyes. But light does not always move forward. Sometimes it turns back. Sometimes it returns to tell us where it has been. Tonight, we drift into the physics of reflection. To the human eye, a mirror is a simple object. It is a smooth surface that shows us our own face. But to a physicist, a mirror is a chaotic dance of quantum mechanics orchestrated into perfect order. When a photon strikes a mirror, it does not simply bounce off like a rubber ball hitting a wall. The process is more intimate. The photon hits an atom on the surface of the silver or aluminum coating. The energy of that photon is absorbed by an electron, causing it to vibrate intensely. This vibration is unstable. Almost instantly, the electron releases that energy by emitting a brand new photon. This new photon travels away from the surface at the exact same angle the original photon arrived. This is the law of reflection. The angle of incidence equals the angle of reflection. It is one of the most reliable rules in the universe. It preserves information. The new photon carries the same color, the same frequency, and the same pattern as the old one. This is why, when you look in a mirror, you do not see a distorted blur. You see a crisp, perfect image of yourself. You are seeing light that has touched you, traveled to the glass, been absorbed and reborn by atoms of metal, and returned to your eye unchanged. Reflection is not just for vanity. It is the primary tool we use to understand the universe. Consider the telescope. Early astronomers used glass lenses to magnify the stars, but glass is heavy and tends to distort colors. Isaac Newton realized that a curved mirror could do the job better. A mirror can gather light from a wide area and focus it all to a single, intense point. The James Webb Space Telescope, currently drifting 1.5 million kilometers from Earth, is the ultimate example of this. Its primary mirror is a masterpiece of engineering. It is 6.5 meters wide, composed of 18 hexagonal segments made of beryllium and coated with a microscopic layer of pure gold. Why gold? Because gold is the most perfect reflector of infrared light. By catching these faint, ancient photons and reflecting them onto sensors, this telescope allows us to see galaxies that formed just after the Big Bang. It effectively acts as a giant, golden bucket catching the rain of history. Even the moon functions as a mirror. The moon produces no visible light of its own. It is a cold, dusty rock. The silvery glow that illuminates your bedroom at night is actually sunlight that has traveled 150 million kilometers to the moon, struck the gray dust of the lunar surface, and reflected back to Earth. It is secondhand sunlight. It is a spectral echo of the day, softened by the journey. This brings us to a deeper realization. Everything you see is a reflection. Unless you are looking directly at a light source, like a bulb, a fire, or the sun, you are seeing light that has bounced off something else. The green of a leaf is simply the leaf absorbing red and blue light and reflecting the green wavelength back to you. The face of a loved one is a mosaic of reflected photons. The world is constantly broadcasting its presence through these rebounding waves, and this reflection happens inside you as well. The human eye is not just a receiver, it is a landscape of reflection. In many nocturnal animals, like cats or owls, there is a layer behind the retina called the tapetum lucidum. It acts like a mirror. When light enters the eye, if it misses the sensors on the first pass, it hits this mirror and bounces back, giving the eye a second chance to catch it. This is why cat eyes glow in the dark when you shine a flashlight on them. Humans lack this layer, but the principle remains. Reflection amplifies reality. It gives light a second chance to be seen. Reflection also allows light to be trapped. In lasers, photons are bounced back and forth between two mirrors millions of times, stimulating more and more photons to join them until they form a coherent, powerful beam. Reflection focuses energy. It turns a chaotic scatter into a directed force. So, light can bounce, it can return, but what if it doesn't hit anything? What if it just keeps going? This leads us to the vastness of the void. It leads us to a unit of measurement that sounds like time, but is actually distance, the light year. In our daily lives, we measure distance in meters or miles, but the universe is too big for these small human rulers. To measure the cosmos, we need a ruler made of the fastest thing in existence. We know light travels at roughly 300,000 kilometers per second. In 1 second, it can circle the Earth 7.5 times. In the time it takes you to snap your fingers, light has already gone past the moon. Now, imagine a photon traveling at this speed without stopping. No coffee breaks, no traffic, no friction, just pure, unadulterated velocity for one entire Earth year. 31,536,000 seconds. The distance it covers is 1 light year. It is a staggering number, 9.46 trillion kilometers, or nearly 6 trillion miles. To put that in perspective, the Voyager 1 spacecraft is the fastest object humans have ever launched. It has been traveling for nearly 50 years and is currently fleeing the solar system at 38,000 miles per hour. Even at that incredible speed, it would take Voyager nearly 18,000 years to travel just one single light year. Light does it in 1 year. This unit, the light year, is the standard brick of cosmic architecture. The nearest star to us, Proxima Centauri, is 4.2 light years away. That means the light you see from it tonight left its surface 4 years and 2 months ago. You are seeing it as it was during the last presidential election cycle. This creates a phenomenon known as look-back time. Because light takes time to travel, looking out into space is literally looking back in time. When you look at the sun, you see it as it was 8 minutes ago. If the sun were to suddenly vanish, we would not know we would still see it shining and feel its gravity for 8 whole minutes. We are always living in the sun's past. When you look at the Orion Nebula, a glowing nursery of stars, you see it as it was 1,300 years ago. You are seeing light that left those stars when the Maya civilization was at its peak in Central America. When the James Webb Telescope looks at the most distant galaxies, it sees them as they were 13 billion years ago, just mere moments after the universe began. We are watching the childhood of the cosmos. The light carries the image of the past, preserving it perfectly across the abyss. This means that history is never truly lost. It is just traveling away from us. Consider this. The light reflected off Earth 65 million years ago, the light that carried the image of the dinosaurs, is still out there. It is now 65 million light years away from Earth. If there were an alien civilization in the Virgo cluster with a telescope powerful enough, and they looked at Earth right now, they would not see humans. They would see a Tyrannosaurus rex walking through a jungle. They would see the asteroid hitting the Yucatan Peninsula. The light from your own birth is out there, expanding in a sphere roughly 20 or 30 or 40 light years wide. The light from the moment you fell in love, the light from your first step, it is all still traveling, drifting through the silence between the stars. In this way, the universe is a giant archive. Nothing is ever erased. The visual history of every event that has ever happened on Earth is streaming outwards at the speed of light, preserved forever in the wave fronts of photons. We are surrounded by these ghosts of light. The night sky is a mosaic of different times. The bright star Sirius is 8 years in the past. The star Betelgeuse is 600 years in the past. The Andromeda Galaxy is 2 million years in the past. When you look up, you are seeing a composite image where now does not exist. You are seeing a museum of cosmic history, all arriving at your eye at the same moment. So, a light year is more than a number. It is a reminder of the scale of our reality. It tells us that we are small in space, but connected in time. It tells us that even across the terrifying distances of the dark, there is a bridge. That bridge is light. It connects the beginning of the universe to the present moment. It connects the nuclear fires of distant suns to the retina of your eye. It connects the past to the future. And as you lie there, drifting through these thoughts, you realize that you are not just an observer of this light. You are a participant. The light reflecting off your face right now will one day pass a distant star. You are sending your own signal into the dark, a silent message that says, I was here. We have spent hours tracing the paths of light across the cosmos. We have seen it bend, reflect, and race through the vacuum. But in every story of light, there is a silent partner, a partner that is often misunderstood as emptiness. Tonight, let us turn our attention to the shadow. A shadow is not simply a hole in the world. It is a physical event. It is the result of a conversation between a photon and an obstacle. When light travels from a source, be it the sun or a candle, it moves in straight lines. When it encounters an object that is opaque, it is absorbed or reflected. The space behind that object is deprived of those specific photons. This creates a volume of darkness. We usually only see the two-dimensional shape cast on a wall or the ground, but in reality, a shadow is a three-dimensional tunnel of darkness stretching away from the object, opposite the light source. If you look closely at your own shadow on a wall, you will notice it is rarely a perfect, sharp cutout. It has a structure. The dark center is called the umbra. This is where the light source is completely blocked. The fuzzy, lighter edge is called the penumbra. This occurs because most light sources, like a light bulb or the sun, are not single points. They have width. Light from one side of the bulb might be blocked, while light from the other side sneaks past the edge of your hand. The interplay of these angles creates the soft gradient of the shadow's edge. This geometry plays out on a magnificent scale in the solar system. Consider the rings of Saturn. To the naked eye through a telescope, they look like solid, glowing disks. But up close, they are billions of individual chunks of ice and rock. As Saturn tilts relative to the sun, these particles cast shadows on one another. During the planet's equinox, the sun hits the rings edge on. The shadows lengthen, stretching across the vast disk, turning the bright rings into a dark, rippling landscape. Or consider the Earth itself. Our planet casts a cone of shadow 1.4 million kilometers long into space. Every night, you are living inside this shadow. Night is not a separate state of the world. It is simply you rotating into the Earth's own umbra. When the full moon passes through this cone, we see a lunar eclipse. The moon darkens and turns a blood red, not because it is generating light, but because the only light reaching it is the sunlight filtering through Earth's atmosphere. Effectively, all the sunsets of the world projected onto the lunar surface. Shadows also reveal the hidden texture of the universe. On the moon, craters near the poles are so deep that sunlight never reaches their floors. These permanently shadowed regions act as cosmic freezers, trapping water ice that has been there for billions of years. In this case, shadow is a preserver of history, protecting volatile chemicals from the harshness of the solar wind. So, shadow is information. It tells us about the shape of the object that cast it. It tells us about the position of the light source. In the case of exoplanets, we find them by watching for the tiny shadow they cast when they pass in front of their parent star, dimming its light by a fraction of a percent. The shadow betrays the presence of the world, but as we peer deeper into the nature of light, the concept of shadow becomes stranger. It leads us back to the fundamental paradox we touched upon earlier, the duality of light. We have established that light creates shadows because it travels in straight lines, like particles, but we also know it can bend around corners and interfere with itself, like waves. This brings us to the heart of quantum mechanics and the duality that Einstein and his peers struggled to define. Let us revisit the photon. Is it a wave or a particle? The answer is not both. The answer is, it depends on how you look. In 1905, Einstein explained the photoelectric effect. He showed that if you shine light on a piece of metal, electrons fly off. But strangely, making the light brighter, more intense waves didn't make the electrons fly off faster. It just produced more of them. Only by changing the color of the light, higher frequency, could you make the electrons move faster. This proved that light arrives in discrete packets quanta. A single blue photon hits an electron with a specific amount of energy, like a billiard ball. A red photon hits it with less energy. This is particle behavior, clear and simple. But then we have the double slit experiment. When we don't look, the photon goes through both slits at once. It acts like a wave of probability. It exists in a state of superposition, a ghostly overlap of all possible paths. It interferes with itself, creating that pattern of bright and dark bands. The dark bands in that interference pattern are a special kind of shadow. They are not caused by an object blocking the light. They are caused by light canceling itself out. The peak of one wave meets the trough of another, and they annihilate. This is destructive interference. It is a shadow made of light plus light. And then comes the measurement. The moment we place a detector to see which slit the photon goes through, the wave function collapses. The superposition vanishes. The photon snaps into a single position. The interference pattern disappears. The quantum shadow is replaced by a classical shadow. This is one of the deepest mysteries in science. It suggests that the universe, at its smallest scale, is not fixed until it interacts with something. The photon is a cloud of potential until a measurement forces it to decide where to be. Does this mean the universe needs a human eye to exist? No. Observation in quantum mechanics simply means interaction. When a photon hits an air molecule, or a wall, or a detector, that is an observation. The environment is constantly measuring the quantum world, forcing it to collapse into the solid reality we experience. This duality is the engine of our modern world. We design lasers using the wave nature of light to synchronize phases. We design digital camera sensors using the particle nature of light to count individual photons, we hold these two contradictory truths in our hands every day. So, as you drift between the concepts of light and shadow, particle and wave, allow yourself to accept the ambiguity. The universe is not binary. It is not black and white. It is a spectrum of possibilities. A photon traveling from a distant galaxy is a wave of probability crossing the void, stretching over millions of light years. But the moment it hits the mirror of a telescope, it becomes a particle, a single point of data that tells us a star was born. You are the recipient of that data. You are the endpoint where the wave collapses into meaning. The light that has traveled since the beginning of time ends its journey in your biology, in your awareness. You are the place where the universe becomes real. We have spent our time together tracing the boundaries of the physical world. We have accepted the speed of light as the ultimate limit, the cosmic stop sign that keeps cause and effect in order. But the human mind is not content with limits. We always ask, what if? So tonight, let us approach the forbidden edge. Is there anything that breaks the rule? Is there anything that moves faster than light? At first glance, the answer is a strict no. Einstein's equations are clear. Infinite energy is required to accelerate mass to light speed. But nature is subtle. While matter and information cannot break the speed limit, there are phenomena that seem to cheat the system. Let us begin with the most intimate experience of all, thought. Close your eyes. In an instant, imagine yourself standing on the surface of Mars. Now, jump to the Andromeda Galaxy. Now, to the edge of the visible universe. Did that take time? Did you have to wait 2 million years for your mind to cross the void to Andromeda? No, it felt instantaneous. This subjective speed can make us feel like consciousness is unbound by physics. But if we look at the biology, thought is actually quite slow. A thought is a cascade of electrical and chemical signals firing across neurons in your brain. These signals travel at roughly 100 meters per second, about the speed of a race car, but infinitely slower than light. The reason it feels instant is that your brain constructs a simulation of the universe inside your skull. You didn't actually travel to Andromeda. You accessed a memory of it. You are exploring a map, not the territory. So, while thought feels transcendent, it is still firmly rooted in the slow, chemical reality of biology. But what about the external world? Is there anything in physics that defies the speed limit? This brings us to the eerie realm of quantum entanglement. Imagine two subatomic particles, like electrons. We bring them together and let them interact in a way that links their quantum states. They become entangled. In this state, they are no longer two separate objects. They are mathematically one single object, sharing a single existence. Now, we separate them. We keep one here on Earth and take the other to the opposite side of the galaxy, 100,000 light years away. According to quantum mechanics, if we measure the spin of the electron on Earth and find it to be up, the electron on the other side of the galaxy will instantly be found to be down. The reaction is immediate. There is no travel time. It happens faster than light could ever cross that distance. Einstein hated this. He called it spooky action at a distance. He believed there must be a hidden mechanism, a secret instruction written inside the particles. But decades of experiments have proven him wrong. The connection is real. The universe, at its deepest level, is non-local. Distance does not matter to entangled particles. Does this break the speed of light? Surprisingly, no. This is the subtle catch. You cannot use entanglement to send a message. You cannot force the Earth electron to be up to signal hello to the galaxy electron. The result of the measurement is random. You only know the correlation after you compare notes, and comparing notes requires sending a regular message at the speed of light. So, causality is saved. The speed limit holds for information, even if the underlying connection of reality seems to transcend space. Then there is quantum tunneling. Imagine a ball rolling toward a hill. If the ball doesn't have enough speed, it rolls partway up and comes back down. It cannot cross the hill. This is classical physics. But in the quantum world, a particle approaching an energy barrier, like a hill, has a strange property. Because its position is defined by a wave of probability, there is a tiny, non-zero chance that the particle is actually on the other side of the hill. Sometimes, the particle simply vanishes from one side of the barrier and appears on the other. It does not climb over. It does not go through. It tunnels. It skips the space in between. This sounds like magic, but it is the reason the sun shines. Protons in the sun's core repel each other because they are both positively charged. They shouldn't be able to get close enough to fuse. But thanks to tunneling, occasionally a proton borrows energy from the quantum vacuum, bypasses the repulsive barrier, and fuses with another. Without this cheating of motion, our sun would have flickered out long ago. So, we see that while the speed of light is a strict law for travel across space, the universe has trapdoors. It has mechanisms, entanglement, tunneling, the expansion of space itself that operate on different rules. Now, let us shift our gaze from the limits of speed to the limits of time. We ask, what was the universe like before light could move at all? To answer this, we must travel back to the very beginning. We often picture the Big Bang as a flash of light, but in reality, the early universe was dark, not because there were no photons, but because they were trapped. Imagine the universe 300,000 years after its birth. It is not the cold, empty void we know today. It is a screaming hot soup of particles. It is a dense plasma of protons, electrons, and photons smashing into each other. In this era, the universe is opaque. It is like the inside of a thick cloud or the interior of a star. A photon is born from a collision, travels a microscopic distance, and then whack, it hits a free electron. It is scattered. It bounces off in a random direction. Whack, it hits another. Light is trapped in a pinball machine of infinite density. It cannot stream freely. It cannot carry an image. If you were there, you would see nothing but a blinding, glowing fog in all directions. This was the cosmic dark age. But the universe was expanding, and as it expanded, it cooled. Slowly, the temperature dropped from millions of degrees to thousands. At a critical moment, roughly 380,000 years after the beginning, the temperature fell to about 3,000 degrees Kelvin. This was the turning point. It was cool enough for the frantic electrons to slow down and be captured by protons. They clicked together to form the first hydrogen atoms. Suddenly, the fog lifted. The free electrons, which were the obstacles blocking the light, were gone. Locked away in neutral atoms, the universe became transparent. In that instant, the trapped light was released. Trillions of photons, held captive for millennia, streamed outward in all directions. This event is called recombination. It was the first flash of the cosmos, the moment the universe opened its eyes. Those photons are still traveling today. They are the oldest things you can interact with. Over 13.8 billion years, the expansion of space has stretched their wavelengths. What started as searing orange-white light has cooled and stretched into the microwave spectrum. We call this the cosmic microwave background, or CMB. It is everywhere. If you have an old television set with rabbit ear antennas, tune it to a channel with no broadcast. Look at the static, the black and white snow. About 1% of that static is caused by photons from the Big Bang hitting your antenna. You are literally watching the afterglow of creation. Scientists map this light with incredible precision. When they look at the CMB, they see a map of the baby universe. It is almost perfectly smooth, but not quite. There are tiny fluctuations, patches that are slightly hotter or slightly cooler by a fraction of a degree. These tiny wrinkles are the most important thing in existence. They represent areas where the density of the early universe varied just slightly. The slightly denser spots had slightly more gravity. Over billions of years, that extra gravity pulled in more matter. Those clumps grew and grew, eventually collapsing to form the first stars, the first galaxies, and ultimately, us. If the early light had been perfectly smooth, gravity would have had no toehold. The universe would be a boring, uniform gas forever. You exist because the ancient light was imperfect. So, as you lie here tonight, you are resting in the aftermath of that first release. The atoms in your body were forged in the stars that grew from those ancient seeds. The static in the air is the whisper of the first transparent moment. We have traveled from the speed of light to the slowing of time, from the bending of space to the trapping of photons. We have seen that light is more than just brightness. It is the ruler of reality, the keeper of history, and the weaver of the fabric we live in. You don't need to understand the math to feel the truth of it. You just need to remember that every time you open your eyes, you are catching ancient messengers. You are participating in a cosmic exchange that has been happening since the first atom formed. You are a creature of light, living in a universe built by it. And in the quiet of the night, that is enough. Rest now in the light that travels and the light that stays. We have spent much of this journey looking upward, tracing the path of photons as they navigate the vacuum of space. In that emptiness, light is the undisputed master of speed. It travels at exactly 299,792 kilometers per second. This is the universal constant, the cosmic speed limit that Einstein established. However, the universe is not merely a vacuum. It is filled with matter, gas, dust, water, glass, and the very atmosphere you breathe. When light encounters these materials, its behavior changes. It does not stop, but it adapts. To understand the physical world, we must look at what happens when the fastest thing in existence meets resistance. Imagine a beam of sunlight traveling from the sun. For 8 minutes, it moves through the vacuum, unimpeded, but the moment it strikes the Earth's atmosphere, and subsequently a body of water or a pane of glass, it slows down. This is not because the photons lose energy. They remain as energetic as the moment they were born. Rather, it is due to the electromagnetic interaction between the light and the atoms of the material it passes through. In a vacuum, there is nothing to interfere with the wave. But in a dense medium like water, the electric field of the light wave interacts with the electrons in the water molecules. These electrons oscillate, generating their own faint electromagnetic waves. The combination of the original light wave and these new delayed waves creates a composite wave that propagates slower than the speed of light in a vacuum. This reduction in speed is significant. In water, light travels at approximately 75% of its maximum speed, roughly 225,000 kilometers per second. In standard glass, it slows even further, to about 200,000 kilometers per second. In a diamond, which is incredibly dense, light crawls at less than half its vacuum speed, around 124,000 kilometers per second. This dramatic deceleration is what gives diamond its brilliance, trapping the light inside for longer before reflecting it back to the eye. This change in speed results in a phenomenon called refraction. Imagine a marching band walking in a straight line across pavement. Suddenly, the musicians on the right side step into thick mud, while the left side remains on the pavement. The right side slows down, causing the entire line to pivot or turn toward the mud. Light behaves in the exact same way. When a wavefront hits water at an angle, the part of the wave that enters first slows down, causing the light beam to bend. This bending is the foundation of all optics. It is the reason a straw in a glass of water appears broken. It is the reason lenses can magnify images. A magnifying glass is simply a piece of glass shaped to bend light rays inward, converging them to a focal point. Your own eye is a biological machine built on this principle. The cornea and the lens in your eye slow down incoming light just enough to bend it, focusing the image perfectly onto your retina. Without this slowing effect, vision as we know it would be impossible. Light would simply rush through us, unfocused and chaotic. Refraction also unlocks the secret structure of light itself. We perceive sunlight as white, but white is not a single color. It is a mixture of all visible frequencies. When white light enters a prism or a raindrop, it bends. However, not all colors bend equally. This is known as dispersion. Red light has a longer wavelength, about 700 nanometers, and it interacts less with the material, so it bends the least. Violet light has a much shorter wavelength, about 400 nanometers, and interacts more strongly, bending the most. As the light travels through the glass or water, the colors separate, fanning out into the spectrum. Red, orange, yellow, green, blue, indigo, violet. Isaac Newton demonstrated this in the 17th century, proving that the colors were not added by the prism but were hidden within the white light all along. A rainbow is simply a massive, natural demonstration of this physics. When sunlight strikes a raindrop, it reflects off the back of the drop and refracts as it exits, splitting into colors at an angle of exactly 42 degrees relative to your eye. Every rainbow you see is a personal optical event created by the specific interaction of light, water, and your viewing angle. We have established that nothing can travel faster than the speed of light in a vacuum. This is an absolute law of relativity. However, within a medium like water or glass, where light has slowed down, it is possible for a particle to move faster than the light is moving in that specific medium. Imagine a nuclear reactor submerged in a pool of water. The radioactive core emits high-energy electrons. These electrons can travel through the water faster than the light waves can. This creates a photonic boom, similar to the sonic boom created by a supersonic jet flying faster than the speed of sound. When a jet breaks the sound barrier, it generates a shock wave of sound. When an electron breaks the light barrier in water, it generates a shock wave of light. This is called Cherenkov radiation. It manifests as a ghostly, brilliant blue glow. If you have ever seen photographs of underwater nuclear reactors, That electric blue luminescence is the visual signature of particles outrunning light in a dense medium. It serves as a reminder that while the cosmic speed limit is rigid in a vacuum, the interaction between matter and energy creates complex exceptions in our everyday world. This interplay of speed, slowing, and bending leads us to a deeper, more fundamental concept. We observe light moving, bending, and traveling. We observe events happening in a sequence. The light leaves the sun, travels to Earth, hits a leaf, and reflects into your eye. The sequence is rigid. You never see the light leave your eye, hit the leaf, and travel back to the sun. This brings us to the arrow of time. In the equations of classical physics, the laws of Newton, and even the quantum mechanics of Schrödinger time is often symmetric. If you were to take a video of a planet orbiting a star and play it backward, the physics would still make sense. Gravity works the same way in reverse. A pendulum swinging back and forth looks the same forward or backward. However, our macroscopic reality does not work this way. If you drop a ceramic mug, it shatters into fragments. You never see fragments leap from the floor and reassemble into a mug. If you pour milk into coffee, it mixes. You never see the mixture spontaneously separate back into black coffee and white milk. This directionality is dictated by the second law of thermodynamics and the concept of entropy. Entropy is a measure of disorder, or more accurately, a measure of the number of ways a system can be arranged. A whole mug is a highly ordered state. There are very few ways atoms can be arranged to make a perfect mug. A shattered mug is a disordered state. There are billions of ways the shards can be scattered on the floor. The universe naturally flows from states of low probability order to states of high probability disorder. This flow is what we perceive as the forward march of time. Energy spreads out, heat dissipates, light radiates outward and does not return. Light is a primary agent of this entropy. When a star burns, it converts ordered matter into chaotic energy photons and scatters them across the universe. Those photons carry energy away, never to return to the source. This is an irreversible process. The sun is slowly emptying its energy into the void. This is why we can see the past but not the future. When you look at a photograph, you are seeing a record of light that was scattered in the past. The light interacted with the film or sensor, increasing the entropy of that system and leaving a permanent mark. The future has not happened yet because the entropy has not increased in that direction. There is no light coming from tomorrow. So, our perception of time is intimately linked to the behavior of light and heat. We are riding a wave of increasing disorder. The light that allows us to see, to grow food, and to exist is part of a one-way flow of energy from hot stars to cold space. This connection between light and time creates the structure of our causality. In physics, we use the concept of a light cone to map out cause and effect. Imagine a flash of light happening right now, where you are. That light expands outward in a sphere. Anything inside that sphere can be affected by the flash. Anything outside that sphere cannot know about the flash yet because the light hasn't reached it. Because light has a finite speed, it divides the universe into things that can affect us, the past, and things we can affect, the future. There are vast regions of the universe that are currently disconnected from us because there has not been enough time since the Big Bang for light to travel between us. We are essentially living in a bubble of causality defined by the speed of light. As you rest, consider the fact that your biological existence is tuned to these laws. Your body uses the breakdown of food, increasing entropy, to maintain its heat and structure. Your eyes rely on the slowing of light to form images of the world. Your sense of now is built on the continuous arrival of information carried by photons. We often think of light as simply brightness, but it is the architect of our reality. It defines the speed at which information travels. It defines the direction in which time flows. It defines the colors we see and the heat we feel. We are adrift in a cosmos that is governed by the simple, elegant rules of this electromagnetic energy. From the nuclear fires of the sun through the vacuum of space, slowing down through the atmosphere, refracting through the lens of your eye, and finally triggering an electrical signal in your brain. The journey of light is the story of the universe interacting with itself. You are the destination of that journey, and in the quiet darkness, as the entropy of the day settles, you are part of the great, forward-flowing river of time, illuminated by the ancient and tireless traveler we call light. We have traveled through the physics of light, from its birth in the atomic fires to its journey across the expanding void. We have seen it bend through glass and scatter into rainbows. We have seen it carry the history of the cosmos to our eyes. But now, we must follow the light to its final destination. We must go to the places where the rules break down. Imagine a place where gravity is so intense that it creates a trap door in the universe. A place where the curvature of space-time becomes infinite. This is the black hole. To understand a black hole, you must forget the idea of a hole. It is not a drain in the bathtub of space. It is a concentration of matter so dense that it overwhelms the structural integrity of the universe. If you were to crush the Earth down to the size of a marble, it would become a black hole. At the center lies the singularity, a point where density is infinite and volume is zero. But surrounding this point is a sphere of pure darkness called the event horizon. This is the point of no return. It is the boundary where the escape velocity exceeds the speed of light. Since nothing can go faster than light, nothing can escape. Imagine you are an astronaut falling toward this horizon. You are carrying a flashlight, sending signals back to a friend on a distant spaceship. As you get closer to the black hole, gravity pulls harder on the light you emit. It drains the energy from the photons. They shift from blue to red to infrared to radio waves. To your friend watching from afar, something strange happens. They never see you cross the line. They see your image slow down. You appear to freeze just above the horizon, your light growing dimmer and redder until you fade into absolute blackness. To the outside universe, your time has stopped. But for you, falling in, time flows normally. You look at your watch. It ticks at 1 second per second. You cross the horizon without hitting a wall. You simply pass from a region where you can communicate to a region where you are alone with gravity. Inside, all paths lead downward. You can no longer move out any more than you can move backward in time. The singularity is not just a place in front of you, it is an event in your future. Yet, even these monsters are not eternal. In the 1970s, Stephen Hawking combined quantum mechanics with general relativity and found a surprise. Black holes are not truly black. In the vacuum of space, pairs of virtual particles are constantly popping into existence and annihilating each other. If this happens right on the edge of the event horizon, one particle might fall in while the other escapes. The escaping particle becomes real radiation, Hawking radiation. The energy for this creation comes from the black hole itself. This means that black holes are slowly evaporating. They are bleeding energy into the cold universe. It takes an unfathomable amount of time, trillions upon trillions of years, but eventually, every black hole will shrink and vanish in a final burst of light. This leads us to the structure of the cosmos itself. We look at the stars and think we are seeing the universe, but we are wrong. We are like people looking at foam on the ocean and thinking the foam is the ocean. The stars, the gas, the planets, the light, everything we can see makes up only about 5% of the universe. The rest is dark. First, there is dark matter. We cannot see it. It does not emit light. It does not reflect light. It passes right through us as if we were ghosts, but we know it is there because of its gravity. When astronomers look at spiral galaxies, they see them spinning fast, too fast. Based on the visible stars, there isn't enough gravity to hold them together. They should fly apart like a carousel spinning out of control, but they don't. Something invisible is holding them in a grip of iron. A vast halo of unseen matter surrounds every galaxy, anchoring the stars in their orbits. It is the invisible skeleton of the universe. Then, there is something even stranger: dark energy. In the late 1990s, astronomers discovered that the expansion of the universe is not slowing down, as everyone expected. It is speeding up. Galaxies are rushing away from each other faster and faster. There is a mysterious energy inherent in empty space itself that is pushing the universe apart. It is acting against gravity. While gravity tries to pull things together, dark energy pushes them away, and dark energy is winning. It makes up roughly 68% of the total energy budget of the cosmos. We do not know what it is. We only know what it does. It ensures that the future of the universe is cold and lonely. This brings us to the final chapter, the deep time. What happens to light at the end of everything? As the universe expands under the pressure of dark energy, the distance between galaxies will grow so vast that light can no longer cross the gap. Each galaxy will become an island universe, isolated in the dark. Inside the galaxies, the supply of gas will run out. The era of star formation will end. The last stars will burn out. The massive blue giants will die first, exploding as supernovae. The yellow suns like ours will swell and then shrink into white dwarfs, slowly cooling like dying embers. The tiny red dwarfs will flicker for trillions of years, but eventually, they too will fade. The universe will enter the degenerate era. The only light will come from the faint glow of cooling stellar corpses and the occasional flash of matter falling into a black hole. Then, even the corpses will decay. Protons may decay. Matter itself may unravel. The universe will be left with nothing but black holes and subatomic particles. Finally, as the eons pass years, numbered with so many zeros that they are meaningless to the human mind, the black holes will evaporate. The last structures of gravity will dissolve into a mist of photons and radiation. The universe will reach a state of maximum entropy, the heat death. In this state, everything is the same temperature. It is just a fraction of a degree above absolute zero. There is no flow of energy, no hot stars, no cold planets, just a uniform, thin soup of particles drifting in the dark. And in this final silence, time loses its meaning. Time is a measure of change. When nothing changes, time ceases to pass. The arrow of time, which was driven by the flow of light and entropy, finally stops. It sounds melancholic, a universe of cold darkness. But there is a beauty in this completion. The universe began in a flash of concentrated energy, a knot of infinite possibility. It spent billions of years unraveling that knot, spinning it out into stars, planets, life, and consciousness. It allowed light to travel, to reflect, to see itself. We are the universe, experiencing that brief, glorious middle chapter. We are the moment when the lights are on. We are the eyes of the cosmos. The light from the beginning, the cosmic microwave background, is still here, washing over us. The light from the future, the final fade, is written in the laws of physics we have discovered. We stand in the center, holding the memory of the past and the knowledge of the end. So, when you look up at the night sky, do not just see the darkness, see the stage. See the vast, invisible structures of dark matter holding the galaxy together. Feel the push of dark energy stretching the void, and cherish the photons that land on your retina. They have traveled so far. They have survived the chaos of stars and the silence of space. They have slowed down in the atmosphere and bent through the lens of your eye to deliver a message. The message is simple. You are here. You are part of the story. You are made of the same energy that lit the first stars and will eventually fade into the final night. Until then, we have the light. We have the curiosity to ask where it came from and where it is going. And as long as we are looking, the universe is not dark. If this journey through light, time, and the cosmos has sparked a quiet wonder in you, consider sharing it with others who might need a moment of perspective. The universe is vast, but our ability to understand it makes us large. Thank you for listening. Sleep well and keep looking up.